And one more moment, and I will kick us off. Okay. Welcome, everyone, to the Zero Knowledge Proofs in ZK Programming and Blockchain Application Development. My name is Sean Bohan. I'm a community architect at Hyperledger. As with all Linux Foundation meetings, this is held under the Linux Foundation antitrust policy. If you have any questions about these matters, please contact your company counsel. If you're a member of the Linux Foundation, feel free to contact Andrew Updegrove of the firm Gesmer Updegrove LLP, which provides legal counsel to the Linux Foundation. This is also being held under the Linux Foundation Code of Conduct, which can best be summed up as be excellent to each other, be kind to each other, be respectful of each other's views. We welcome everyone to this workshop, and we cannot thank you enough for joining us, but also, this is open source. Please consider getting involved. This is permissionless innovation. Anyone can work on these projects. Anyone can use this software. Anyone can use this code. And we really appreciate the community that helps build these projects. And part of that community are two fantastic presenters, Andras and Daniel. And I'm going to stop sharing and turn it over to them.
Awesome. Thanks a lot for the introduction. Let me just give a shot and share my screen. And if that works again.
It looks good.
I would just start basically the presentation. So basically, hey, everybody, good morning, good afternoon, and good evening, depending on the time zone. My name is Daniel, and with Andras, we're just going to give practically a workshop on zero-knowledge programming. Perhaps just a little bit on our background. So we are practically I'm more like an engineer, software developer. I have some background in economics as well. But I'm definitely not a mathematician, and I'm definitely not a cryptographer. Andras is more like a hardcore software developer, a lightweight mathematician and cryptographer as well. So he's gonna have the opportunity to plunge more into the cryptographic and really zero-knowledge mathematics part. But from my side, I'm more like a software developer, so I will just focus on the how should I put it, the software part of zero-knowledge programming and the more programmatic parts. We are practically independent contributors here, so we don't advertise any companies. We just advertise ourselves basically. So it's like free contribution from our side to the Hyperledger community and to the world. So that was like brief introduction from our side. So let me just plunge a little bit into the agenda. We're just gonna start with like zero-knowledge basics. That's gonna be from my side. It's gonna be like basic zero-knowledge without mathematics. Then Andras will give like a more mathematics and in-depth presentation on zero-knowledge, including some figures as well. I hope there's not gonna be like much proof and theorem, but I'm not quite sure. Again, that's gonna be like more mathematics and cryptographic involved. Then we continue with like more on software development path. So if you're a software development and you want just to use like zero-knowledge programming, so we just continue with zero-knowledge programming with Circom. Circom is a zero-knowledge programming language which can be used, pretty practically. Probably not by anyone, but like by programmers with like relative good cryptographic understanding. Then we're just gonna have some programming examples as well. You will find a GitHub repository for that. I'm just gonna show basically a link for that. And then we gonna plunge a little bit into the details of zkRollups, of zero-knowledge rollups. For the first round from a theoretical basis, and then we just gonna see one demo for that basically. The original idea was that we do like more zkRollups, but basically we just figured out it's practically impossible to cover zkRollups and zero-knowledge programming and Circom in a 3-hour session. So that's almost impossible, I would say. So we're just gonna cover the basics on a high level, and I think that will be enough practically for the end. So for the workshop repositories and prerequisite, again, so the first at least 1 hour gonna be presentation mostly, and then we do some programming. You can follow us with programming. If you want to follow us with programming, what you practically need to have, first, we use Visual Studio Code. You can use Atom or something else as well, but I mean, the demonstration is gonna be with Visual Studio Code. We use Circom. There's a link for that, so you need to install Circom. I just installed globally, so I got the Circom and SNARK.js globally on my environment. We use Fabric samples. I guess, I mean, if you're familiar with Hyperledger technologies, then probably Fabric samples is one of the, I mean, key repository that people use. Then we use Remix Ethereum. It's an online integrated development environment, which is gonna test some smart contracts with Remix. Basically, the idea was that we wanted to show something which is zero-knowledge programming and which is compatible somehow with the Hyperledger stack. And if I say Hyperledger stack, we meant of two things. One is like Fabric. For that, we will just use the Fabric samples. But the other like integration point is Besu, Hyperledger Besu. We just don't use Besu at the moment because it's just, I mean, if we got one laptop, if you use like if you install Fabric and Besu on one laptop, it's just pretty much infrastructure heavy. So instead, we're gonna show in Remix, again, that's a Solidity integrated development environment, how a Solidity code for the integration looks like. So practically, it's not directly Besu, of course, but again, that's a Solidity smart contract, which is like compatible with Hyperledger Besu as well. And we got one workshop repo. This is the last one. It contains like 3 big scenarios. One is like hello world Circum programming with Hyperledger stack. The second one is like a more complex programming scenario, and the third one is practically a very simple zKRollup. So that's basically somewhere. So if you just take a look on it, that's basically my GitHub repo. So you will find basically the 3 examples here that I'm gonna demonstrate. So that's the plan, and I don't know. I mean, I would propose I would just continue with the presentation, and perhaps we just stop like in every 20 minutes or every 30 minutes, like having, I don't know, 5 minutes break answering questions, or perhaps we will have like once a 10 minutes break somewhere in the middle where we try to, I mean, get some coffee, of course, and try to answering questions. Basically, that would be my proposition. And then basically, so at the end we can have like questions and answers. It's a little bit questionable from our side how it looks like from a timing perspective. Honestly, this is the first time that we make this workshop, so I'm not quite sure how much time will we have at the end. But if we have some time, we can likely have like, I mean, bigger discussions on zero knowledge, on Hyperledger technologies and stuff like that. So that's the plan. And I would say, let me just start with a very high level introduction to zero knowledge proof. So basically, if we say like zero knowledge proof, we mean something which is a proof, which is kind of a proof of a statement. But this is not necessary. So for the first one, it is not absolutely similar to a classical mathematical proof. So it is not like, I mean, proving the Pythagoras theorem. It is a little bit different. It is, I mean, mathematics is involved, but again, for the first intuition is not like a classical mathematical proof. It has 2 differences. For the first one, I mean, if we say like we want to have a proof, zero knowledge proof, we usually imagine that we get like 2 actors. It's like Alice and Bob. I mean, if you're in cryptography, you always have Alice and Bob. So here in cryptography, so we have these 2 roles for the first round, Alice and Bob. And basically, if we say like proof, we mean that basically Alice wants to prove something for Bob. That's what we mean. And so there are like three differences comparing with, I mean, for the first one, there are like three differences comparing with a classical proof. The first difference is that we get these two vectors. So this is like more like cryptography and not like classical mathematics. The second one, this proof can have kind of an interaction. So we can imagine basically that interaction means that Alice and Bob communicates with each other, and there's here a sequence of communication. So like Alice says, hey, I know a solution. Bob says, hey, prove this solution. Then Bob sends some challenge and some responses, and perhaps there's some more challenges and more responses, and so on and so forth. So basically, if we say like proof or zero-knowledge proof or such a proofs, then what we mean usually is that there might be an interaction of messages between Alice and Bob, and basically, as a result of this interaction, Bob will be convinced that Alice basically knows something. Perhaps I just forgot to emphasize basically the idea for such a zero-knowledge proof that Alice proves something for Bob, that she knows something, she knows practically a fact. And this proof looks that way for the first one, it can be interactive. On the other hand, it might have something which is like practically a stochastic attribute of this proof. So we can say that Alice knows something, and Alice wants to prove for Bob that she knows something. But I mean, this proving process, which might be interactive as well, might be probabilistic, stochastic as well. So it means that after some interactions, at the end of this interaction, Bob might not be 100% sure that Alice really knows a fact, but perhaps Bob can be like 99% sure that Alice knows some fact, basically. But perhaps if you have like more interaction, then Bob gonna be like 99.9% sure that Alice knows something. If we have like more interaction, Bob can be like 99.99% sure that Alice knows something, and so on and so forth. And basically that we have just a couple of examples. It's like one example is like this Sudoku. I mean, this is a game. You get these columns and these numbers, and you just have to fill out somehow with numbers that somehow the addition of these rows and columns is equal or something similar. That's like a Sudoku game. So if we speak of like such a proof, Alice might want to prove or might want to convince Bob that she knows basically the solution of such a Sudoku puzzle. That's kind of a proof. And then we say that this proof is zero knowledge if Alice can convince Bob that she knows, for instance, the result of this Sudoku game in a way that the result itself will not be revealed. So practically at the end of this proving process, which again might be interactive, might be probabilistic as well, Bob will be sure that Alice really knows the result of this Sudoku puzzle. But Bob will itself not know basically the result of this Sudoku puzzle. So that's the first. I mean, that's the basic idea for zero-knowledge proofs. Again, so the idea is we get usually two roles: once a prover, once a verifier. The prover wants to convince the verifier that she knows a fact without revealing that fact practically. And then this convincing process, which we say as a proving process, or we might say as a proving process, can be on the one hand interactive, on the other hand probabilistic. So basically, Bob will be sure that in 99.99% that Alice knows the result of this Sudoku puzzle, but again, Bob will not know basically the result of that Sudoku puzzle. So that's the first, I wouldn't say it's definition, but it's like, I don't know, it's like the first idea of a zero-knowledge proof. And we have just two very intuitive examples. these are non-mathematical examples, rather just building intuition that such zero knowledge proof is really possible. It's not something wild for the first run. And the first game is like find Waldo. This guy is here, Waldo, and we got a picture here full with people. So basically, Waldo should be somewhere on this picture. And then let's just imagine we got like Alice and Bob, and Alice wants to convince Bob that Waldo is on the picture, but without revealing the exact location of Waldo. That's, for instance, a very intuitive zero knowledge proof. So the question is how it can be done. I mean, there might be like two solutions. One solution is like, again, we just stay with the physical world. It's a non-mathematical example. So let me just imagine that we just print out this picture. Anyway, I think Waldo should be somewhere here, but honestly, I'm not 100% sure. So let me just imagine we just print out this picture. It's gonna be a piece of paper printed on this picture. And we just have another picture, which is like 10 times bigger than the original one, and it's white. And we just take this big picture and we just make a small hole, which equals to the head of Waldo, and we just cover this big piece of paper. We just cover with this big piece of paper the original printed picture. So if we do so, what we see that we see a big white paper and we see a small hole, and on the small hole we basically see the head of Waldo. So we can be sure that basically Waldo is somewhere on the printed picture. But the point is, as the cover paper is like 10 times bigger than the original one, we are not sure which is the exact location of Waldo. That's like one example. The other one we can do in another way as well. Again, let me just print out physically this picture on a piece of paper. Let me just turn this paper and let me just sign it. Sign it a lot of times. Let me just have a couple of like small signatures on the other side of this paper. So if we have so, we can just, I mean, Alice just can cut out, for instance, the head of Waldo from here, and then show this small head basically for Bob. And then if Bob turns practically the picture, then he can see the signature, for instance, on the other side. So he can be sure that this small Waldo head was cut out from the original paper, but he's not sure what was exactly the location for that. So again, that's the intuitive example. The second classical example is the cave of Alibaba. It's more like an interactive proof. Again, we got Alice and we got Bob, and we got a cave. There are like two directions in this cave. That's like direction A and direction B. And then somewhere at the end of the cave, we have a gate. That's like a magic gate, and there's a password. A magic password, a magic word, and if anybody knows this magic word and says this magic word, then this gate will be opened, practically. Okay, so the idea of this game is that Alice basically wants to convince Bob that she knows this magic word, but in a way that Bob will not know basically the magic word itself, but will be convinced that Alice knows for sure that magic word. So one way of playing is this game that like Alice just goes into the cave and chooses one direction randomly or as she will, A or B. Bob is still outside the cave, and then Alice just goes into the cave in the direction of A or in the direction of B. So after that, Bob comes here and goes to the place of Alice, and Bob decides if Alice should come back in the A direction or in the B direction. So there might be like different possibilities of doing it. So there might be a possibility that Alice went to the A direction and she doesn't know the magic word, and then she comes back in the A direction. Then Alice has luck, basically. then there might be a possibility that Alice went to the A direction, but Bob says, hey, come back from the B direction. Then Alice can come back from the B direction only if she knows that magic word. And on the contrary, there might be the case that Alice goes to the B direction, and Bob says, hey, Alice, come back from the B direction. Then Alice might have just luck, so she can just manage this puzzle without actually knowing the magic word. But there might be the chance that Bob says, hey, Alice went to the B direction, but Bob says, hey, come back from the E direction. In such case, Alice come back only from the E direction if she knows the magic word, and then she can open basically the gate with that magic word. So what's tricky is this is like a probabilistic setup. So Alice might have like 50% chance that she can manage this puzzle without knowing the magic word. But if we just repeat this experiment, then again, and then in one experiment, Alice has 50% that she can manage without knowing, but basically 50% basically that she has to know the magic word in order to manage this puzzle. So the point is, if we repeat this experiment, then basically Alice has smaller and smaller chance to manage this puzzle without knowing basically the magic word. I mean, you can just imagine if it's like, we just repeat 2 times 66 experiments, then Alice has like 0.25% that she can manage the 2 puzzles without knowing exactly the magic word. If you repeat just 3 times, then it's just 125 and so on and so forth. So basically, this is a kind of an interactive probabilistic proof, because there are like many interactions, and basically based on the interactions, the chance for Bob really knowing that Alice knows the magic word will be increased, will be surer and surer, but it's not gonna be basically 100. I mean, it's never gonna be like 100%. So that's a second interactive example and intuitive example. I'm just having like a couple of applications very fast, and then we can just continue with the more theoretical and more precise formulation. So it's like, for instance, one application which is a non-blockchain one for zero-knowledge proofs is like I mean, there are many fake pictures on the internet. So how we can be sure? I mean, and especially with the AI, there are just more and more fake pictures on the internet. So like how we can be sure that, for instance, a picture which is on an online media is not fake, but it's kind of real. So one way is like having a digital camera and having like a kind of a signature and private key, and then signing the picture with like a public private key cryptography, making sure that that picture was really taken by a trusted camera, for instance. That's possible. However, the problem is that these pictures are usually not published in an original form, but they are transformed practically. So you can imagine that, like the picture is going to be smaller or bigger, or the colors or the resolution will be changed. It's due to the online media. So how we can be sure that we have like a modified picture, but despite that was like taken by a camera which is trusted by some public private key cryptography, for instance. So what we can do, for instance, we can do like zero knowledge proofs for this transformation, and then if we just have like at the end kind of a picture which is again probably was changed in size, in resolution, in colors, but despite if we have not just the original signature from the trusted camera, but the zero knowledge proof for the picture transformation as well, then we can be sure at the end that this is practically a picture which was taken by the original camera and was transformed basically in a trusted way. Again, this is like a non-blockchain usage. Just 2 very brief examples. One example is like, I mean, if we are in blockchain, one very big application areas is like using private blockchain transactions. So for the first round, blockchain privacy is challenging. It's simple because you got like many independent nodes, and then nodes can nodes should validate your transaction because that's a distributed ledger. They should validate the transaction independently from each other. And the easiest way to validate the transaction if they see the transaction. But that causes some privacy issues, of course. So the question is, how can independent nodes validate the transaction without seeing basically the transaction content? And that's possible with like zero knowledge proofs practically. That's one example. The other example that we're gonna take a look more a little bit like in details, that's so-called the rollup. It looks that way that if you are in blockchain, executing an application in the blockchain, is challenging because it's usually slow. There can't be many transactions executed parallelly, and then basically it's costly as well. Especially if you're on a public blockchain. So blockchains have scalability issues, and one way of just overcoming these scalability issues is just executing transactions outside the blockchain, which is possible. But the problem is with that if you execute transactions outside the blockchain, then you have practically a counterparty risk. So basically, you have to trust the guy who executes these transactions outside. Otherwise, the whole trustless setup practically vanishes from blockchain. So how it can be done? Not to have the counterparty risk. One way of doing is like executing these transactions outside the blockchain, but basically having a zero knowledge proofs at the end that these transactions were really executed in a correct way, and then putting back that proof of the correct execution in the blockchain. That's what basically zkRollup does. So that was basically the first very intuitive presentation, I would say. So from a very high level perspective, that's a very exciting field. I would say that there's gonna be like at least like 15 more years active development. I'm sure about. For the first one, it was very much influenced by cryptographers and mathematicians. But I would argue that slowly we have like tools and frameworks that are available on the engineering side as well. So slowly, and I would say slowly, so perhaps not fully, but slowly it will be actually available for programmers as well, perhaps not average programmers, but programmers with like cryptographic knowledge. And that was the first intuitive presentation. I'm not quite sure how shall we have like 3 minutes? I would say we can answer like 2 questions. Just like
we have 1 or 2 questions in the chat. Go for it.
So let me just browse and probably chat. Yeah, the difference between SNARK and SNARKs, we're gonna just cover that later. Programmatically,
I will talk about that.
Yeah, we're gonna talk about that. Yeah, I would say, it's just a mistake from my side. Yeah, the video gonna be available. Actually, it's on the YouTube. Yeah, so it's right. There's one question like Bob should actually have an idea about what could be the solution. So basically, it looks like these games looks like there's a setup at the beginning. So we assume at the setup that both Alice and Bob knows the game. Basically, they have they share the basic ideas. They play the same game. There's like a setup and knowledge sharing basically at the beginning. Yeah, absolutely. Yeah, I would say we got very nice technical questions, but I hope we're gonna answer them during the more detailed mathematical and programmatic course. And then I will just give it to András, and then let's continue with the more in-depth mathematics.
Okay, thank you. Wow, yeah, first of all, I really thank you for participating, and let's get started. So I would just continue your presentation with some of the properties of the zero-knowledge proofs. Probably the most three important one. I just collected here. The first one is soundness. We call it soundness because it means that everything that is provable on that system or with the zero-knowledge proofing system is true. If you just remember for the Waldo problem and looking for Waldo or the Sudoku problem, I will talk about the Sudoku problem later, but if you just remember, Alice proof systems are truthful and do not let her cheat. So for example, Alibaba cave or the other Waldorf's problem, you can't cheat it. You can't cheat in that system. So everything is provable, is true. So if you prove something, it means it will be true. The second one is completeness. It means that there is, if something is true or everything is true, I would say everything is true, it should have and it has a proof. So it means if we think about the previous examples, Alice can convince Bob that she found Waldo because she can cut out Waldo and can show to Bob. So Bob must be convinced. The third one is zero knowledge. Okay, probably zero knowledge. It's really important now for us because it means that if I know something and I would convince someone that I know that knowledge without revealing my knowledge to the other person. So that's why zero knowledge, because my sentence or my proof does not lead or leak any information to the other side. So if we think about the previous examples, Alice just cut off Waldo from the paper and give to Bob, but Bob can't reveal any information about where was found Bob by Alice. So it's really important, the soundness, completeness, and the zero knowledge part or zero knowledge properties of these proof systems. Okay. I know today a lot of people would like to hear about SNARK and STARK and the generic zero knowledge proof systems. This is the last one, but we have a lot of types in this field, and I really would like to show you that zero knowledge proof systems and zero knowledge proofs are much more than the SNARK and STARK. First of all, we have interactive types and non-interactive types. Daniel already talked about these ones. I will show you more examples with mathematics. There are statistical zk proofs. I won't tell anything about them because Daniel already told a lot of things about. They are usually in interactive ways and with statistical probabilistic. The simple, I call it simple or purpose-based proof of knowledge. It's really interesting because the third one, this one, is you can use everywhere in your application if you would like, or you can create your own proof system as well. So that's why I think it's really important to know about this. It's really a simple one. I will show you. There are bullet proofs. I really wouldn't like to talk about this one, maybe later because it's a little bit complicated. And see the Sigma protocols or generic zero knowledge proof systems. These are the most common ones like STARK and SNARK. And I'm going to talk about a little bit of these. Okay, let's get started. What does it mean interactive? Interactive, you probably yeah, Daniel talked about. So I really don't want to just repeat. Here's another example, an intuitive example of like Alice and Bob. Alice, it now returned that in a colorblind world, Bob would like to convince Alice that he knows or can see the colors. So the statement really is that Bob, I can see colors. The setup, Alice holds in her hands red and blue balls, and Alice challenges Bob which hand contains the red ball. If Bob can tell, then it's on the left hand, then Alice, it's okay. Then Alice just secretly change the balls or not change, it depends, and then show again to Bob her hands, and then Bob can tell if Alice changed or not the balls. So at least at the end, Alice will know this with this challenge response. They do many times, then Alice will know that Bob can see colors or not with a high probabilistic. Okay, my favorite one is the Sudoku problem. It's a non-interactive way. So here is now a Sudoku, and Alice wants to prove that she solved this Sudoku problem. It can be any kind of Sudoku. It may be an impossible Sudoku, but also Alice would like to solve this, and her statement is that she knows the solution for the Sudoku. So Alice, for this, Alice will build a proof machine or a machine which can be used by Bob to check the solution or the statements. Okay, and now I will show you what this proof machine will work, or how does it work. Okay, first step, Bob or Alice, it doesn't matter, just put the initial numbers on the machine. The machine contains the same as the Sudoku, like all rows and all columns. And Bob or Alice, it doesn't matter really, just put the initial numbers with cards with numbers, and the numbers are phased up. Okay, like here, like 3 and 9, 7, 3, 6, 9, 8. So it's really important, 3 cards face up for each one. Then Alice secretly, for the next step, Alice secretly just plays her solution 3 times. Every place has 3 cards with Alice's solution. Okay, but face down to the grid. So after it, Alice put all these cards here into the machine. They will lock the machine, okay, and Alice will give to Bob. So Bob can't open it, just can play something with the box. And now what he can do? Now Bob, starting with each row, I put here. Bob just start with the first row and push the button, and the machine will give 1 card from each each column of that row to Bob. So now Bob has a lot of cards here. Okay, and of course it says it's randomly choose the cards, but the box can randomly just put the cards here. Okay, now we repeat all the steps. Okay, all the rows and all the columns. So we finally remaining cards store into one packet. I think maybe yeah. Okay, so finally, if we just put here 9 cards here, everywhere is 9 cards here, and we down here we do the same for all columns, then we will have 9 rows and 9 columns, and each grid will contain 9 cards as well. Okay, so at the end we will have 27 packets, I think we could say that. Okay, so after that, the Bob or the machine just can shuffle the cards, and then Bob flips all the cards later. Flips the cards and can verify that each packet contains all the numbers 1 through 9 without any numbers missing or duplicated. If it's true, then Bob can be sure that Alice knows the real solution of that Sudoku puzzle. So actually this is a non-interactive way, because Alice and Bob should not talk about anything. Alice can do whatever she wants, and after it, Bob can just verify the solution with this machine. Okay. Okay, simple zero-knowledge proofs. What are these? These are usually built only for one purpose, so it can be used for any type of statements to prove with zero-knowledge properties. What are these? We have some, we called it accumulators, ring signatures, proof of knowledge, and this is the 3 main types. I will talk about accumulators and proof of knowledge. Proof of knowledge is really interesting one, and also the accumulators. Usually nowadays they are elliptic curve based or lattice based. Lattice based solutions are currently assumed quantum cryptography or quantum computer safe solutions or quantum computer resistant algorithms, the lattice based solutions. The elliptic curve based solutions probably of course we know that it's not anymore safe for a quantum computer. Let's do some math for this one. First, I would like to share you or show you proof of knowledge. So let's say we have some knowledge, and with this knowledge we can always we can always turn or make a large numbers. Okay, so we can make just the information just like a number representation. We can call it like A. It can be a secret key or any other information that we would like to encode or just show that we know that information. So we could say this is the secret information. In the world of elliptic cryptography, it can be a large random number or any secret information. So the first thing for this A, we can create a public key part or the public information of that secret information. Now, what we can see here in elliptic curve based, we always have a generator point. It's usually, we call it G, and modulo P means P is a prime number. So we use the modulo arithmetics here as well. I hope you understand this a little bit, because I did not prepare any slides for the basic mathematics of modulo arithmetics. But if you think about your hour at home or clock at home, like not the digital one, you have from 1 until 12. You have numbers on your clock, and every day the clock just turns 2 times, so it means modulo 12 o'clock is. Okay, some properties of this arithmetic in elliptic curve based mathematics, and usually almost all the current cryptographic primitives and all the cryptographic private public environment, we have some kind of properties like these. It's really similar for the elementary mathematics, so it's really easy to remember for the properties. It's like, okay. So let's say this is an interactive way, and Alice would like to convince Bob that she knows an information, a secret information like A, okay? So here Alice will choose A or calculate A or just knows A and calculate the public part of A with this then Alice can send Bob, and Bob knows this statement. We call this is a statement because Alice just make it public, this key or this public information. Then Alice choose a random key after publicating the private part of A, public part of A. Now she choose a random key number, a random number, and create a public part of this key, and we call it commitment. Now Bob knows this public key as well, or public part of this key. Of course, in cryptographic, it's very important from this public information for pKa and pKk, Bob can't get any information about A or key. Okay, it's very important. With a quantum computer, of course, Bob can calculate the private informations from these, but with a computer, you can't. Okay, in an elliptic curve-based environment, of course. If we use lattice-based algorithm, then you can't count the private parts from these. Okay, now Bob will choose a random C number and send to Alice. This calls the challenge, okay? Now Alice can calculate S, and S is the proof. We can, I don't know, I just maybe should call it P, but modulo P, so that's why I choose S, calculates S. It's like A times C plus K, and it's modulo P. And then sends this Bob. This is the proof, okay? And now Bob can check whatever these equations are equal to each other, like the generator to the S, like creating the public part of the S. Okay, Bob can really do this one. And then calculate with the public keys and with the C, which is the challenge, can do this mathematics and can check if it's true or not, it's equal or not. If it's not equal, it means that Alice does not know A. Okay, if it's equal, it means Alice knows A. So the secret key. Why does it work? I just put it here because so it can be sure, and you can really just make sure how does it work. So how can this was an interactive way. Now I really would like to show you how can we make this in a non-interactive way. Okay, we usually if we talk with a cryptographer or at the university, we just call it the Fiat-Shamir transformation of the algorithm. So it's if you find out something which is interactive in zero-knowledge world, you can easily turn it into the non-interactive way with these transformations. Here, I just put it here. Alice knows A and create the public key. It's the same. Alice choose a random number. This is the commitment. Okay. Sorry for changing the variable names. It's sorry, really sorry, but it's used to like this one. So that's why I use this signs and letters. Choose the number, the commitment, okay? And now Alice will create her own challenge and not Bob, okay? So it means Alice will calculate C. We should, it's really important that we should use hash function, a cryptographically good hash function. We will put GA and the two public key, the public parts of the secret key and the commitment, and we concatenate them and then create a hash code of that, and this will be the challenge. Now Alice can calculate the proof and can send all these to Bob. So after it, Bob really can calculate everything. So the verifying process, and if Bob calculates these equations and can check that the verifying equations is equal to the PKV. If it's equal, it means that Alice knows A, really, okay? This is one addition and one more important, I think it's a more important and very important note, that if when Alice sends Bob the proofs and all the numbers, Bob has to save C to somewhere because Alice maybe can, or not Alice, maybe some person just can listen Alice and Bob what they are talking about, and maybe that person, it's like the intermediate person, can later come back to Bob and say, hey Bob, I know A and here is my proof, and Bob calculates and everything is okay, and Bob will think that the intermediate person is really Alice, but it's not. So that's why it's really important now to that Bob must save C, and if someone for example send to him proof to verify, Bob can check whatever he see or see that C number or not. If Bob did not see the proof before, then it will be okay and can verify all the proofs and can be sure that there is no an intermediate man. There are a lot of other solutions to prevent this one, but would like to talk about this currently because it's not about not related to zero knowledge systems. So it was a really interesting one. For this mathematics, it's really easy to implement. It's just a few lines of code, and I will show you some implementations later in a GitHub repo. Okay, so now let's go to accumulators. It's really almost the same that we. Okay, previously we can use any elliptic curve based solutions. It doesn't matter if it's a Ethereum, not Ethereum, but Ethereum used that or Bitcoin used parameters for that elliptic curve or any other. For the accumulators and zero knowledge accumulators, it has a mistake here. It's BLS12 curve, so not BL12, BLS12 curve. It's a little bit slightly different from the previous ones and what Ethereum and Bitcoin blockchains uses, because BLS12 has two cyclic groups or cyclic groups, G1 and G2. With the accumulators we would like to use, for example, it's really a good question, what can we use the accumulators? For example, I would like to convince someone that I put the information into the system, okay? And later, if you read the system and all the informations, you can check whatever the information is in the accumulator or not. Furthermore, I can tell you, for example, I have this information. The information has a public key, a public part, so I don't have to tell you the information. It's enough. For example, I know only the hash code or a public part of the information. And then I can prove someone that I put the original information into the system without revealing the information. So that's why zero knowledge accumulators are really interesting ones. One really good properties of the accumulators, their size are constants. That's constant size. It means it doesn't matter in a block. In a blockchain world, every block contains a Merkle root and Merkle proofs nowadays. But with accumulators, it's more efficient because it doesn't matter how much transaction can be found on a block, because the accumulators are just constant sizes. So compared to the Merkle proofs, its accumulators are a little bit better one if we think of the size of the data. Okay, let's get through and do some math again. So first of all, we create a secret or random number like S key, and we create the public part. G1 is the generator of G1 is the generator of G1 cyclic group or cyclic groups. We can calculate the public part of the secret key. So we initially the accumulator's initial state is this G1, okay, the generator point. After it, we would like to add some information, call it Y1. We can do like this, okay? A1 is like equal, so the new state of the accumulators equal Y1 plus the secret key multiply with the generator point, okay? After it, we can add the Y2 data. You can see here the second equation. Now we would like to remove any data from the accumulator is also possible. If I know the secret key, I can remove any data from and create a new accumulator state with removing this one. It's also possible. Okay. So the accumulators, let's say we would like to create a proof. Okay. Because now we just created the accumulators with states, and any information we can calculate the accumulators with any additional information. But now I would like to create a proof that for the information is really in the accumulator. So now initially A is the accumulator value, the most current accumulator value is known. Okay. It represents A. Now, I would like to show or prove to someone that I know Y1, the information, and I put it in the system, and also I put it in the accumulators. It's called a W, and you can calculate like this one. Okay, and then I can show to everyone the W, and also the accumulator value is also publicly available. So now everyone can check this equation. I did not tell about E. What is E? E is a non-degenerative pairing function in elliptic word. The math behind is really hard. I think it's really interesting, and I would like talk about it like 2 hours, but we don't have much time. So I just, believe me, this pairing functions really exists, and also they are good, and we can use them. And there are a lot of libraries you can use to calculate these equations. So it's really a good one, and it's really a fast one. So it's much faster than the Merkle proofs, even the calculation and the verification as well. And here are the just the solution of why does it work. Okay, let's talk about SNARK and STARK. What is SNARK? Okay, SNARK is a zero knowledge, succinct, non-interactive argument of knowledge. Okay, I think the name should show everything about what is it. It's really interesting what the pros and cons. Pros, what are the pros? It has a small proof size. Really, it's a really good one. Fast, it's generic. SNARK is generic and trustlessly verified by anyone. Okay, so you don't have to trust when you verify the proof itself. And because the proof size is small, you can use it in a blockchain world really well. The other side, or the downside of SNARK is really hard, the trusted setup. Because at the beginning, when you creating the SNARK system, you have to use some random numbers, and if these random numbers are known to anyone, it means that anyone or that person can create false proofs, or can do any kind of proofs that he or she wants. So that's why it's trusted setup. It's really an important one in SNARK world. We have, probably Daniel will talk about the tau a little bit. It's in this word we use tau to solve this trusted setup issue with SNARK, because SNARK is really a good one. So what's the other downside? because it's based on elliptic curved cryptography, it's probably not quantum safe algorithm. So a quantum computer or quantum computing attack is probably achievable. Okay, setup and proof generation is process intensive. It's usually time and or space complexity is high. It means if you stay with us and with Daniel when show all the programming stuff, you can see by yourself that setup and the proof generation is sometimes really slow. So that's why probably Daniel already created will generate or start to generate a new proof system. It would take half an hour, I think, or something like that one. It depends on the complexity of the zero knowledge. It's really, oh yeah, it was just something with the internet. So it's really complicated and time consuming to create a proof generation system or a SNARK system, the setup system. What is STARK? Because of the SNARK downsides, a lot of cryptographers and mathematicians and other guys just wanted to make a better system. So they created STARK, a zero knowledge, scalable and transparent argument of knowledge. The good part is there is no need for a trusted setup. The fastest, this STARK is really fast, so much faster than SNARK. And it has higher security. It's quantum compute, it's resistant to quantum computing. What is the downside? Really large proof size, like 10 or 100 times bigger, okay? So if you say the SNARK has like 1 kilobyte data, then STARK may be 100 kilobyte data, the proof size. Lower adaptation, I will show you some diagrams and all the stuff to compare the STARK and SNARK. These are probably the most important ones that you should know about STARK and SNARK. I really don't want to deep inside the mathematics behind it. It's really complicated. One of the slides I just will show you at the end, like this one, the deep dive. It can be 5 minutes, 5 hours, 5 days, or like a 2 weeks course just for this one slide. So it really depends how deep knowledge would you like to have in a mathematical way. But this is a programming course, so I really don't want to make things just hard for you guys. Okay, zkP systems. If you can't see the lines, we will share all the presentations so you can check all of them. As you see, almost all is SNARK based. I will show you, here is a bulletproof one, and here is 2 STARK at the end. Okay, so every other zero knowledge proof systems are based SNARK based. Okay, and here are some properties of the system, each of them. So if you would like to use any zero knowledge proof system of these, you can check from this table and all the parameters, and then just go and check yourself what you need and use them. Okay, SNARK and STARK, the drawbacks and what I'm already talked about it. STARK is always the orange or red ones. Okay, so it's really really shows every diagram that the prover time is much lower than the for STARK than SNARK. The complexity for STARK is much lower. It's logarithmic the scale, so it's really important. This is a space complexity in kilobytes, and verify time. It's really important. It's also logarithmic, so you can see that STARK is really the verifier time just doesn't make any sense, so it doesn't count. For the SNARK, it's really going up. It's like hours, okay? So it's 1 second here, okay? And this is now a really huge one. Okay, the last one, the last slide. Probably Daniel will continue with this one. So I really thank you for your patience, and I would give to Daniel the stage. And if you have any questions, that let me know.
I would generally say, we can stop like for 2 minutes and then answer like 2 questions. Probably that's.
Wait. Oh, sorry. Yes. Yeah. Okay. Okay. Wow, a lot of questions. Good questions. Okay. Okay. Oh, a lot of questions. Okay.
Yeah. So what we're gonna probably do is we are just browsing the questions, and then we just again answer like few selected questions. Especially we just select the question that we can answer.
Yeah. Okay. This is a good one. Does the zk hiding property in bilinear pairing comes from point correlation from one cyclic group to the other? There is no correlation, I think. So you can't decide from one cyclic group with the pairing based. It's like a one-way pairing. Okay, so you can't know which was the original to point from the cyclic group when after you do the pairing. Okay. Oh, it's a huge one. Okay. Yes. I think it's wait because okay. So here, okay. It's really a long one. So the zkSNARK hiding property in bilinear pairings indeed comes from the point correlation between the two cyclic groups. In more detail, bilinear pairings, such as the Weyl pairing of the Tate pairing, are defined over two cyclic groups, G1 and G2, of the same prime order P. Yes. These same prime order, yeah, it depends. Okay, but now let's say, okay, these pairings have the property. So the pairing like E, G1 and G2, like pairing G1 and G2 equals pairing G1 with H multiple by the pairing value of G2 and H. In this case, it's really important to emphasize that H in this equation, H1 and H2, because it's not the same group element, cyclic group. So G1 and G2 generators, okay. and H random element in G1. Okay. Now I know what are you talking about. Yes, the hiding pointer zkSNARK comes from the fact that the pairing operation hides the individual element of G1 and G2, making it difficult to extract any information about them from the pairing results. Yes, this is what I'm talking about as well. This, I don't know the guy name or a woman. I really don't. Elizabeth, yeah, Elizabeth. She's really doing very well on the comment section and the chat section. This was not a question. Yes, I understood, but maybe your graphics said differently. So which is correct? SNARK, longer setup but faster execution. STARK, fast setup but slower execution. No. Okay, STARK. Okay, STARK is fastest. Okay, and no need that fast setup. It doesn't make any sense. Just a trusted setup. Okay, for the SNARK, longer setup means the generation of the whole proof generation is slower. The proof generation for STARK is fast, but the fastest, but with a large proof size. So that's why it's problem. Okay, the graphic says, I will show the graphics. The prover time, okay, you can see here how fast is to create a proof. Okay, this one is the orange, the proof time, the prover time. Okay, so the question was asking that the prover time shows no, it doesn't. It's not different. Okay, or I really don't know what. Maybe I missed something. Okay, communication complexity and verifier time. Yeah. Okay, thank you. Yes, there is no more questions. I really thank you.
Okay, awesome. So how do we do it? We can have like, I don't know, 5 minutes break, or I can continue with the next session. It's gonna be like probably 20 minutes again.
Whatever you're comfortable with, Daniel.
Yeah, I would propose let's just
again,
continue. Then.
Yeah, let's just continue. But I want to say thank you once again to the folks in chat who are answering questions. Really great stuff. Really appreciate it.
Yeah, absolutely. That's just hard questions.
Elizabeth was really did a good job.
We can answer only the half. Yeah, absolutely. Yeah. Absolutely great questions. Yeah. So then let me continue again with a couple of slides, and then this is gonna be more like zero knowledge programming again. This is gonna be more like the programming stack again. So I would like just to continue where András stopped practically. So what we have here basically is SNARK. Usually we have just SNARK, but again, if we have something else as well, then it's, I mean, the general idea is pretty similar on the programming level. So again, I'm not mathematicians. So basically, if you say SNARK, that's called succinct, which means that's a short proof. It's much smaller than the original problem or the original computation. Usually we prefer non-interactive because the problem is if you are in blockchain, just imagine what we want to achieve, for instance, that all the validators can basically validate our transaction in a way that the transaction itself is not visible, just a zkSNARK, just a SNARK proof on that. So basically, we want to have it in a non-interactive way, because if there's such a SNARK proof, everyone should just get it, should just say it, hey, that's valid or non-valid, without doing much interaction. So in blockchain world, we like non-interactive proofs. It's argument of knowledge that's practically someone knows the information, the prover knows the information. And then this can be zero knowledge or non-zero knowledge as well. Basically, it's important to note that even if like we have a SNARK, which is practically a short proof that the computation was executed in a correct way, it might make sense if that's not zero knowledge, because just imagine you get a complex computation and then you just make kind of a short proof that this complex computation was executed correctly, that you can validate practically on a slow computer. And it sounds funny, but blockchain exactly is this. So if you have like a smart contract in a blockchain, that's a small computer, that's a slow computer. And then if you do something off chain, that's a huge, I mean, that's a more performant computer. And if you just want to validate something that was executed off chain, then you can do it with a SNARK, even if that's not zero knowledge. Anyway, but we more like zero knowledge, especially because I mean that's the, I mean, that's the title of the course. So in a simple computation model, what we usually do, we just try to implement a function. Okay, I mean everything is a function, of course, but we just try to implement a function which has some public and private input, and then this is not gonna be even a function; it's gonna be a predicate, so it will be evaluated to true or false. And usually what we do in zero-knowledge programming, we implement this function, and the implementation is a little bit tricky because sometimes zero-knowledge programming languages are tricky, simply to say. Okay, but that's what we want to do, basically. So as a programmer, as a software developer, usually we don't start with, like mathematical proofs. But there's already something which is kind of a zero-knowledge engineering flow or programming flow, I would say. And it looks that way that you see on this slide. So basically, we start with a domain-specific language for SNARK proofs. And again, if I say domain-specific language for SNARK proofs, I mean domain-specific language is a special language which is like special syntax basically and semantics as well. And if I say for SNARK proofs, basically that's what we want to implement. We want to implement kind of a predicate or kind of a function which has some public, some private input, and it evaluates to true or false in a simple way. So that's what we have as a domain-specific language. And then it abstracts away some of the more complex mathematical forms. So usually this domain-specific language is compiled to a more mathematical way, to a more mathematical format. It's like a zk-friendly format that's like a rank 1 constraint or kind of other formalism, which is more can be interpreted by a kind of a zero-knowledge automatic prover. And then this compiled output is practically put to a zero-knowledge framework. And then basically there's some parameters, and then we just get some proof practically at the end. So basically what we do as a developer, we just try to implement our logic, which is kind of a function or predicate, in a higher level language, and then we just use kind of an environment which on the one hand compiles this one to more mathematical forms, on the other hand creates like proofs and creates a verification of proofs. So that's what we want to do in an engineering framework. And there are already domain-specific languages, and there are like frameworks for this one as well. Here are some like DSL programs like Circom. If you ever heard of like Socrates, Leo, Zinc, I'm not quite sure, Cairo, Noir. Some of these frameworks are pretty highly hyped. For instance, recently, some of these frameworks are older, but basically old means here like, I don't know, 3-4 years old. So some other consideration as a developer, which proof do we want to use? And then again, even if I'm not a mathematician, but I mean, despite I just need to understand on a high level what we use and what are the implications of this practically. So basically the things that should be considered, which is the proof size that I want to use, which is the verification time that I want to use, which setup do I have, and if I have something which is quantum resistant or not. And then there's even like proof creation time as well that might be considered as well in some scenarios. And we got some options. There's no like perfect options, but we get usually some choice. So the classical one is gross 16. It's again just without going into the details. That's like a zero knowledge proof system, and then basically it has a pretty small proof size. Why this is important? It's because we use blockchains. So basically, so friends of me said a couple of years ago that if you think of blockchain, then a blockchain kilobytes are big data. It's because, I mean, all of the data that you write into the ledger, it stays there. All of the newest version is gonna stay there, and basically it is replicated to all of the nodes, basically. So again, anything that we want to evaluate on the ledger and practically write into the ledger should be as small as possible. It's because, I mean, kilobyte is big data in blockchain context. So that's the proof size. Of course, verification time is very important. So it should be, again, small. If we speak of like the blockchain context, then we think of like block time. So we need like a verification time that is in a block time. Otherwise, we will have some problems. Another characteristic is setup. Basically, there's like a setup process before each zero knowledge proofs, and then it's generally the question how much the setup procedure requires a centralized component. And of course, if we need like centralized components, that's bad. It's bad because we just want to be decentralized and trustless. And if we despite have like kind of a trusted setup component, that's usually not so optimal. And of course, the last parameter is quantum resistance. It's perhaps we might as well have like, I don't know, 10 years before it's getting to be a real issue, but I don't know, perhaps even in 5 years, we might have some problems with that. And these are some of the possibilities. It's like row 16s, like Blanc. We got like bulletproofs and SNARK as well. These are not actually SNARK systems at the end, but basically, I mean, it gives you a good basis comparing these algorithms. So again, we got the proof size. Again, it's very optimal by gross. We got the verification time. It's very optimal by gross. It's not so optimal by Blanc, for instance. And it is getting to be slower and slower if you go to like SNARK. But like if you take a look on setup, so for instance, gross 16, the earliest or the most famous probably core algorithm has like trusted setup per circuit. That means that for each and every different circuit, that's practically each and every different function, we just need to have like a trusted ceremony for setting up and generating some of the cryptographic materials. Blanc is better. We need just one universal setup, and that can be used for many circuits. I mean, on the one hand, it's good. On the other hand, it's bad because I mean, if that universal setup is compromised, that's actually bad luck for all of the possible circuits. And then we get like transparent setup. At transparent setup, we don't need this centralized setup at the beginning. It's just practically fully decentralized. And we got quantum resistance as well. So for instance, SNARK is believed to be quantum resistant. All the others examples are not, for instance. But again, there's no best solution. There are like different solutions that can be used for different scenarios. So that's one consideration. The other consideration is basically more practical and more like engineering. Like we have different frameworks, and then different frameworks might actually support different like core zero knowledge algorithms. So for instance, if you use Circom, you can use gross 16 and you can use Blanc, but you can't use for the first one bulletproof or SNARKs, which it is not supported out of the box. Basically, you want to use a framework that supports these core algorithms out of the box, because I mean you don't want to like necessarily be a cryptographer and implement on your own, but you expect like that you use a core framework that has like gross 16 and Blanc, basically. So another practical thing is which framework, which is the framework that we use, which language it supports. It's like Noir is Rust. Many people love Rust. Many people don't really love Rust. So it's a question if you love it or not. Circom is like a hardware description language. SNARKy.js is like JavaScript, and so on and so forth. So it's a little bit the question is which programming language you prefer. And then there are some other perspective as well. So for instance, if you have like a zero-knowledge framework, which are the integrations that are supported more or less out of the box? Again, you just don't want to develop everything from scratch. So practically, if your environment supports, so for instance, if you develop a Rust-based solution, then of course, I mean, you probably just pick one framework which supports Rust out of the box, which is even written in Rust and programmed in a Rust style language, and so on and so forth. If you don't use or you don't like Rust, but you use like Solidity, then you probably pick a language which has like, you know, simple integration possibility with Solidity, and so on and so forth. Perhaps one more consideration, usually we consider in a tool selection the life cycle of these tools. It's because you know, I mean, some of these tools are very much hyped, which is, I mean, on the one hand, it's a good thing because that's, you know, super cool and new, and all the cool guys use that framework. But putting that into a productive tool development is sometimes tricky. It's because, you know, they are just too early stage, and then the tool has a lot of bugs. The framework has a lot of bugs, so it's just a struggle to develop it with it. So you can use like tools which are not so much hyped at the moment, but, you know, more stable placed on the market. Again, there's no very much like very stable placing on the market because the oldest languages, I don't know, are 5 years or probably 6 or 7. So these are not, that's not an old technological stack at all. So let's see Circom. We're gonna take a look on Circom, and we will integrate Circom with Hyperledger Fabric and with Solidity as well. Circom is a domain-specific language. It's DSL actually. There's a typo, but anyway, what we program like low-level arithmetic circuits and rank 1 constraints. So it's a pretty low-level language, which is, yeah, I mean, on the one hand, not so simple to program, but on the other hand, it's just, you know, I mean, you are just closer to the realization. So you can more optimize your software. You can just understand much better what you develop and what you don't. It was used, like, for instance, in Tornado Cache as well, which is in some sense, in a good example, in some sense, it's not such a good example. Anyway, it supports Grow 16 and supports plug. I would say it's well established. It's like exists more than 4 years, I would say, which is an old tool in this fastly developing blockchain world. And it gives you integration possibilities. So it gives you a good integration with JavaScript, that's SNARK.js, with C++. It has a Solidity verifier as well. And then we're just gonna, with the JavaScript integration, we're just gonna integrate with Hyperledger Fabric as well. Okay, so basically that's the high level structure. We just do some high level circuit. We just define it in the circuit domain specific language. We just compile it basically. We will do a trusted setup. This trusted setup gonna be modified a little bit. There are some trick that's called the power of tau, and power of tau makes this trusted setup, which is a centralized setup, more decentralized. So makes it a little bit not so trusted, more trustless, I would say. And then we get like some proving key, some verification key, and then basically we just put some input into our calculation and the proving key, and then we create a proof basically, and then the proof can be verified with the verification key, with the validation key. Then that's really a correct computation that was based by our inputs, and then some of this input can be visible, which are public inputs, and some of the inputs will not be visible. These are the private inputs. Again, so we program this model. We're just gonna program practically a box, which is a function which evaluates to true or false in our case, which has like public inputs and private inputs, and that's what we're gonna program basically. And then in our demonstrations, what we're gonna take a look on the next, I don't know, more than an hour, is that we will create proofs of an offline computation, and we will import this offline computation proof to blockchain, and we will verify it in blockchain. That's what we want to achieve. So regarding the code that I'm gonna show you, that's the scenario. That's always the scenario. There's a setup at the beginning, of course. And for instance, the proving key and the verification key are distributed right at the beginning, I would say. And there's some power of those setup as well. But basically, we can imagine like two scenarios. Again, this is like the off-chain world here. So what we're gonna do, we do some back-end calculation, for instance, but we can do actually front-end calculation as well. Again, so like creating the proof can be time-consuming as well. So if I just come back to this table, one question, one column, which is not on the table, how much time does it take to create the proof itself? It's because we might as well create proof from the backend as a backend computation, but there are examples as well that we create this proof on the front end. It's like there's like a famous game for that. That's like Black Forest, if I'm not mistaken. And in Black Forest, you just create the proofs in the browser in the front end. So basically, the proof calculation should be as fast as possible as well. But nevertheless, if we have like a backend calculation or a front-end calculation, we just create a zk proof out of it, and then we just send this proof in a transaction. And the two scenarios are we just make some chain code verification in Hyperledger Fabric, and then we can make some chain code verification in Hyperledger Besu as well. Okay, so I would say that was like the presentation for the development part, and then we will continue with coding. However, I would say let me just have like 5 minutes break, and then we continue with coding based on this setup, if everybody agrees.
That's fine. If we want to take a 5-minute break, give folks a chance to get a cup of tea or take a bio break, and we will come back in 5 minutes.
Awesome.
Thanks, Daniel. Hey, Daniel, would you mind terribly stop sharing just in case?
Yeah, absolutely.
We are not going to stop the video recording because that is just going to cause a problem, but I am going to put up a screen. We'll be back in 5 minutes.
Yeah, absolutely.
All right. Okay.
Yeah, so we're back. I'm back. We can continue if everybody's ready.
I think let's give everybody one more minute and then we can restart. And I just put some quick reminders in the chat. We are recording this. We will send out a thank you note to the registrants. The slide deck and links and video will be on the wiki page. I'll share all the links again in about 15-20 minutes. And thank you again, first of all, to everybody who's joined us. Secondly, to our great presenters. This has been fantastic. But also to everyone in the chat who's sharing their knowledge and helping out. It is really appreciated. I will turn it back to Daniel. You've got it.
Okay, thanks. So let me continue. That's what we want to achieve basically. We just want to do some offline computation. Again, that's gonna be JavaScript. Theoretically, you can do it from the back end. Theoretically, you could do it something similar from the front end as well. You create a zero-knowledge proof, and then you just want to verify that zero-knowledge proof on the blockchain, either with Hyperledger Fabric or with Besu. We just gonna stay very much with Hello World. There's one repository that I'm gonna use. It is theoretically shared. It has 3 examples. One is a Hello World. Second one is a more modular Circom, and the third one is a very simplified rollup. So that's what I'm gonna show basically. If you go into each and every repository, you will find basically a more detailed description what's happening. So that's what I will follow. So if you want to follow me, if you have like Hyperledger Fabric prepared, then and Circom installed, then basically you can just follow me. So basically what I did, I just copied this repository and I start with Hello World. If I start with Hello World, the most important part of such a zero-knowledge programming is the programming itself, I would say. So what I'm doing here, I'm just implementing basically circuits. It's kind of arithmetic and rank 1 constraint circuits. So basically, this is like, I'm not quite sure if I have sketch, but let me just give you a sketch. Anyway, I just forgot to mention we will have like less slides and more demonstration. But basically what I'm doing with like zero-knowledge programming, I just create a circuit which has some inputs, which has some, that's input 1, that's input 2, and it has some output as well. And it can have something. So it can be like an arithmetic circuit. Then we have like plus, and then we can have like a third input. Then we will have some multiplication as well. And based on that operators, we have something which is an output. Okay, so practically that's what we're gonna here do. In this very simplified Circom demo, I have 2 inputs. One is an input A, and the second one is an expected cube, practically. Okay. These are like input signals. Again, this is like a circuit programming language. It's kind of similar to a hardware programming language. So what I'm doing here, I will have one intermediate signal as well, and I will have one output signal as well. It doesn't necessarily to use it, but I will have it. So what I'm doing some calculations. I just say that this internal variable is like A times A, and then we got this cube, which is an internal variable, which says it's like A times this internal calculation. And then we just say that we have the expected cube, which is cube. So practically what we do here is a very simple circuit for saying, hey, this input, we just multiplied three times. So we just have the cube basically of this input parameter. Okay. Basically we can have like 2 parameters. One is like kind of arithmetic. So basically we can have like multiplication and addition. So that's what we have usually. And then what we usually do is like we do like rank 1 constraints. Rank 1 constraints looks that way that I have a variable and this variable equals or must equal, this free equality means it must equal to like variable 2 times variable 3 plus variable 4, for instance. Okay. So that's what we call as a rank 1 constraint. And then we can have rank 1 constraints and practically additions. Usually we use both if we have circuits. So in this sense, what we have, I have a calculation, and then practically this calculation circuit must be like A times A. We can have like different circuits and different calculations as well, but perhaps it's not so important for the moment. Okay, so what we're gonna start with is like writing or implementing the internal logic of a circuit, of a calculation that we want to execute as zero knowledge, which has like inputs, something with the calculation model, which is like, again, very simple. It's addition and multiplication. It's practically like rank 1 constraints. And what we want to do at the end, we just want to somehow define which are the input variables and which are the public input variables and which are the non-public input variables. Okay, so what I'm having here, I just put here expected Q. So basically, it looks that way, that this is a number which is a cube of a number. So I have A that's like, I don't know, it's like 3, then the cube is basically, the expected Q is, I don't know, 27, if I'm not mistaken. And then basically, I just prove that this 27 has basically a cube root without explicitly defining this cube root. Okay, that's a very simple computation, basically. So what I'm gonna do, first I'm gonna go to run. I just implemented some script. I will just run this script. It will do a lot of things. First, it will just compile my Circom soft program. I mean, again, this is my Circom program. It will be compiled. Then practically there will be basically a witness generation. There will be a power of tau ceremony. Again, what I will use here is Plonk, and Plonk requires a trusted setup. So basically, what I'm gonna do with this, I mean, it's actually the SNARK.js library, but SNARK.js library has a power of tau ceremony. So what I'm efficiently do, I just make this trusted setup more decentralized. So it looks that way, power of tau, that basically what I need to do is to create somehow one secret. I just need to create one secret. This is one secret. But the point is, if I just create this one secret in a centralized way, that's certainly a counterparty risk. And if I cheat with creating this secret, then practically I can prove wrong statements as well with zero knowledge proofs. So what's happening with this power of tau ceremony, that there are many independent actors creating, these are like different people creating this secret, and then each contributing somehow to this secret. And then it looks that way, that if any of these people, contributors, are honest means that, for instance, they really generate randomly the secret, then the result secret will be practically random as well, will be correct as well. That's what we call the power of tau. So I got here a power of tau ceremony. I will just create a 12-bit key or 12-bit keys, and I will have like, I think, 3 contributions. That's like the third contribution. Sometimes there are some random keys as well. It's called random text, so it's actually not so random, but it's just a demonstration that basically Circom supports this power of tau ceremony. And I will just aggregate this. I will have a final power of tau, and based on this final power of tau, I can set up Plonk. Plonk is a zero knowledge proof system, and if I set up this Plonk, I will have practically my proof. I can create my proof, my verification key, and my proving key practically. And at the end, I just create a Plonk proof, and then I have just one verification as well. Okay, nevertheless, I will just run this stuff. And let's see how fast it is. So what I'm just doing, I just go to hello world. And then I will just run this script. Let me just zoom a little bit. So I will just say run.bash. So again, what it does for the first run, it just compiles my circuit into actually like a more interpreted way of the Circom proving system. So I would say this is actually the high-level way of programming in Circom. Perhaps not so high-level than with a normal procedural language, but it is high-level enough. So it just compiles the circuit. This part is basically the power of tau ceremony for the trusted setup. I just have some random text. Sometimes I just already put this in this random text. So actually you find this contribution, this random text. Sometimes what's happening is that's the power of tau ceremony. It's just kind of a fast Fourier transform. I'm not quite sure why. Anyway, it can take a while. I think in this example, if we use like 12-bit long keys, then it's gonna take like 1 minute. I hope it's gonna finish in 1 minute. If you use like bigger keys, so for instance, in our last example, the key size is like 18 bits. Then the power of tau ceremony might take like 3 hours on this laptop. This is just like a simple laptop. And then, so the key size is important as well. Actually, the key size depends on the circuit size as well. So if you have like smaller circuits, then it is enough if you generate just smaller keys. If you have bigger circuits, you actually need to generate like bigger keys. So it can be like a little bit tricky. Again, if you have like very big circuits, then basically you need to have like very big keys, and then again, just generating these keys with a correct power of tau ceremony might be challenging. But slowly that should be finished. No, there's one more round in power of tau. But actually that should finish like in a minute. So don't worry. Anyway, if I just finish it, let me just take a look on the run script. So what I'm having in the run script at the end, again, this will be the final power of tau. So after the final power of tau ceremony, I will just set up Plonk. And then what I will do, I will just create I just export the verification key, and then I will create a proof that's gonna be with SNARK.js. So that's like the built-in environment. And then basically I will verify this proof as well. Again, like the verification will be done by the verification key, by the public JSON, and by the proof itself. Just perhaps one thing to show. Yeah, it's finished. So theoretically, I have my proof. If I just go to this subdirectory, everything is under this demo1.js. So if you just browse in the files, we see here basically these are the power of tau ceremony files. There were actually a proof generated as well. It's just perhaps important to point out. I mean, this one is the proof. It's just a little bit tricky. Wouldn't go very much into the details because partly I don't understand here everything. But basically, what's more important, we get like an input.json, and the input.json is basically the input of the circuit, which might contain public and private inputs as well. So in this example, we just implemented this circuit in a way that basically it has like one input, which is A, and one expected cube, which is expected to be the cube this input, and basically we just implemented in a way that expected cube is public, but the original number is not public. And what we see here, we get an input.json. It correctly shows basically we get both the inputs. We get both the private input and the public input as well. And that's what we use practically as we generate proof. But if we verify the proof, what we're gonna do, we're gonna use just the public inputs. So basically, we just gonna use the proof and the public inputs. We have this public input 2 times. It's because I have not just the expected output, but there's an output as well. So one is the output, the other one is the expected output, which are practically equals. So I have this guy 2 times, but perhaps that's important to note. Then in a verification process, we just use the public input. So efficiently, if we just verify this, that we verified that there was a cube root of this number, and we can be sure that there's a cube root of this number without actually knowing what exactly the cube root is. Actually, the cube root is 99, but the verifier won't know this. It will know just the public input. Okay, this is a very simple example. Let me just take a look. If I just take a look on README, I have everything basically in README. So basically, after having my proofs and verifications key and proving keys, I will show 3 directions of somehow integrate this zero-knowledge proof into a real environment. One is a very simple Node.js. So what I can do, I have here a proof.js, and basically I have here a verified.js. These are practically written by me, but basically that uses the Circom libraries. So basically what I use from SNARK.js long full proof. I will have just the inputs, actually that's the vast, and the proving key. And with that, I will create a proof. Again, I will use here the inputs, and I have a verify as well. So verify will again use basically nothing special, but the verification function of SNARK.js, and it has the verification key. It has the public inputs, not the private inputs, and it has the proof. And based on that, it just gives back if that's a valid zero-knowledge proof or not. So that's I'm gonna show here, and then let me just again I will just use README. So this was like the run generated practically everything. So let me just generate a proof with Node.js. And what I will do, I will just generate a proof with Node.js. That's the proof again. It's just generated by Node.js, and we got the public signals as well. And again, it's important to note that the public signals has just the cube, so not the cube root itself. But you know, I mean, with this public signals and with this proof, the verifier should be able to decide that this guy really has like a cube root without actually knowing the cube root itself. So I can make the verification as well. It's nothing special. It's basically the Node.js call that I show you. So I just use that one. So what it gives back like a verification result, which is true at the moment. So nothing surprising. It's just, you know, basically zero-knowledge proof is not so fancy in a way that there's a lot of struggle, and at the end, basically what you get back is either true or false. That's in most of the cases. So it's, you know, not so fancy in some situations. But again, this is like one integration possibility. It's a non-blockchain one, but we can use it with blockchain as well. So the second integration possibility is with Solidity. What I will do, I will just go to this subdirectory. Again, practically everything was generated here. And what I will do, I will basically generate a Solidity smart contract. SNARK.js has basically a function which is like, I think, export Solidity verifier, probably zk export Solidity verifier. But anyway, based on this guy, it creates a verifier.solve. So what's happening here is that what I have is a verifier.sol. That's a Solidity smart contract. And then let me just copy out this guy. So if I just open Remix Ethereum, what I can basically here, that's my newest zkdemo.solidity. So what I can basically do, I can just copy paste this code. Again, that's a Solidity verifier code. It was automatically generated. It has a lot of cryptographic material. It has the verification key as well. And again, I'm just not sure. We're not gonna go very much into the details. For that, we would need like another workshop. But from a system integration point of view, what we have one function, which is a verify proof, and it needs like two inputs. One is the proof itself, and the other one, that's the public signal. So it's a pretty simple stuff. What we do, we can call basically a Solidity function, which is verify proof with the proof and with the public signals, and it gives back us basically a result if it's true or false. That's what it does basically. So let me just give a shot, and then let me just basically try out. What's the problem with that? Yeah, that's the problem, is that this should be like so. Yeah, so that's a live demo. If I have a live demo, everything goes wrong. So I have just compiled. Theoretically, there's a warning. It doesn't matter. So what I'm basically doing, I'm just have the zk demo. This is our zk demo. I just deploy it to this development environment. And what I'm having is one function. That's one function. That's a verify proof. That's basically this guy here, which is actually a simple view function somewhere. Yeah, that was here. That's verify. That's basically, that's like a simple view. And what I can do, if I just go back to README, what I will have here, we got this SNARK.js.generate call. That's again, that's a Circom functionality. So what I can do, I can just generate a demo call. And the demo call is generated with the help of the already generated proof and already generated public signals. So what we have here, that looks complicated, but basically that's the proof. And then these are the public signals, and the public signals are just 2 times this cube here. So that's like the public. That should be actually 2 times and in a hexadecimal form. Okay. So if I have this form, then what I can do basically is to put that here to verify proof and say verify proof, and then basically I just got the result that should be true. Okay, but just to checking if I'm not cheating, so if I just have this guy and then I say like just modify a little bit, then basically if I just put this one, and then that should be a false. So that's a false proof. Okay, so that's basically the idea, and then you can integrate with anything you want. So basically, if you use this contract, then you can integrate with any kind of on-chain functionality that you wish, basically. So one question is how much gas it costs. Basically, it costs like 200, almost 60,000 gas. So it's not cheap. But as an example, if you use like Hyperledger Besu, it's basically not critical. Even in, in Ethereum that's expensive, but like even on Solidity, on Polygon, you can manage that kind of amount of cars. If you're like on a consortium Ethereum network like on Hyperledger Besu, then shouldn't be such a huge problem. So it's not cheap, but not extreme. Okay, so that was the second kind of integration. Again, we just created some calculation. We just made one way, basically, just in JavaScript. We just sent basically the proof and created a verifier in Solidity that can be used with Besu. And the last integration possibility is with Hyperledger Fabric. So let me just show how it works with Hyperledger Fabric. What I'm basically doing here is that I have a very simple FabCar example. If you're familiar with like Fabric, you have this basic. You have this. If you're familiar with Fabric, there are a couple of examples in Fabric samples, and one example is this FabCar. It's a very simple chain code where practically you can create cars. These are the cars. The cars can have different colors, can have a type like Toyota, Prius, that's a model, and some owners like Tokomo, Brad, Jean, Max, and so on and so on. So that's what you have, and then there are some functionality is like you can query the cars, you can create new cars, you can query all cars, you can change the car owner, for instance. And what I extended I just extended this guy with like a verification, with like a verification function. It looks that way. It's a verify function which uses similarly the SNARK long.js verify functionality. Again, it's JavaScript, so it's easy to integrate. I just need to have the verification keys. I just need to have the input JSON, and I just need to have the proof. Okay, so what I'm gonna do here is that first I just extended this FabCar example with a verification function, and then I just extended this change car owner as well with actually two commands for practically verifying this zero-knowledge proof. So the idea is kind of similar that let's just imagine if I know basically a secret, then I can change the car owner. And if I can prove basically with a zero-knowledge proof that I know that secret, then I can change the car owner. If I don't know the secret or if I can't prove it, then basically I cannot change the car owner. So it's kind of again, very simple demonstration, but kind of zero-knowledge proof-based authorization mechanism for this car owner functionality practically. So what I'm gonna do, I just cheat a little bit. I just need to have the proof. That's the proof. And normally that's not something that I should do, but I will just put the proof into the contract. Okay, you shouldn't do it normally in a normal application because basically proof should be sent basically from the backend or from off-chain components. I just do it in a way because if you're familiar with Fabric, it's just not so easy to send a transaction to Fabric in a way that it contains a lot of such structured information. It's just a little bit tricky. So I will just simplify things and I just put the proof basically in this contract, and I just need some verification keys as well. So I just have the verification keys, and these are the verification keys basically. So I will put the verification keys as well in Fabric. That's gonna be the FabCar demo. And these are the verification keys. So that's the verification key. And again, what I'm having is like one Circom environment functionality, which is SNARK.js. I just call Plonk, and then I just make a verification. Okay. So what I'm doing is not very nice, but works for the time being. What I'm gonna do here is that I will just copy this one to Fabric samples. Okay, so basically, if you are familiar with Fabric samples, under Fabric samples chaincode fabcar JavaScript flip, you have this fabcar. I just didn't prepare it, in a more sophisticated way. What I'm gonna do, I just go to these Fabric samples under Fabric samples chaincode fabcar JavaScript. Anyway, everything is just documented in the README, and I will just copy this fabcar there. Okay, that's nice. So the next step is that we just, again, I just go back to the README because everything is generated, everything is documented. So basically, we are at the Hyperledger Fabric integration. We just want to make sure that Fabric.js has the latest vks and proofs, and copy the modified Fabric.js to the Fabric samples /chaincode /fabcar /JavaScript. Okay, so after that, we just start basically the Fabric network. Sorry, just some technical. So let me just go to, that's Fabric samples. So I just go to test network. And what I'm gonna do, I will just start basically this test network in a very simple or very normal way. I just create basically one channel. So that's like the usual setup. It just takes a while, but practically that's normal with Hyperledger Fabric. So I just created actually my Fabric network. I get just the couple of peers, orderer services. Yeah, it's just, I think that's a two organizational setup. And what I'm gonna do, I will just install this fabcar. Again, I will use basically the chain code that I just modified. So that's what I'm gonna do. And again, it might take like 2 minutes until we get this ready. Especially the installation might take a couple of 10 seconds, but I mean, it's just usual with Hyperledger Fabric. So in the meantime, perhaps let me just take a look on if I can continue with the slideshow. I have one slide about this power of tau ceremony. It's nothing special than a decentralized setup ceremony. Again, the problem is if you have like a trusted setup, that's not very optimal. And the reason is for that because, I mean, blockchain, you don't like trusted setups because you have to trust somebody that basically like generated a true random. And then at the end, just drop like, private keys or stuff like that. So you don't like it. And for instance, if that's not true random, then basically everything can be hacked or everything can be proved. So basically what you do with power of tau, you just make a trusted setup, or you just make the trusted setup more trustless. If I can say it, that there are many contributors, and basically if not all cheat, then your result will be practically trustless. Usually there are independent contributors. So like, I know in a couple of like public networks where this is really important, there are like couple of hundreds of independent contributors. Of course, like coordinating them is not necessarily the easiest, but it's working. And again, if one contributor is honest, then the result will be good. So like true random, for instance. So I just have it. If I see it, I have just created basically my chain code. And again, in my chain code, what I'm having is basically the modified fabcar. So let me test it. Testing in Hyperledger Fabric is not so easy because you need all the environment variables. You just need to have like certificate authorities, reference to membership service providers, just creating the necessary transactions and putting to the network. But I have just created everything. So basically, this is my setup. And let me just test if I can do it. For the first round, what I do, I just query all my cars. So basically, that's like querying all cars. At the moment, I don't have any cars. So let me just create one car. It's one transaction which creates a car. It's going to be like an ID. That's car 11. It's like Nissan, Leaf Green, and then Shibohan is probably the owner. So I will just create this transaction. So that should be great. It says great. So if I now ask all of the cars, then what I'm having is that I have one car. So I just clear it and then ask again the cars. Basically, I have one car. That's the owner is Shibohan. Okay. So let me have like this verification. Again, what I'm gonna do, I just call the verify function that I place basically in the chain code, and I will just use the public inputs. Again, normally I should use the public inputs and the proof as well, but in Fabric, you know, I mean, just having this command prop stuff is a struggle. So even with like, you know, like the two public numbers, you just be sure, make sure that this /hash stuff works well. So if you just want to put the whole proof, it's gonna be more struggle. So I have basically the proof in the smart contract itself. It's a little bit like cheating, but that's the easiest way to make demonstration. So it says true. So that's what I have. Let me just take a look if I can hack it. So for instance, if I want to verify like something else, so if it's like 8, then it's false. So it works as expected practically. I can verify the correct public input again with the proof, but if something is wrong, like the public input is something else, then I cannot verify. Okay. And then basically what I have here is like change the owner with the proof. Again, I will call the change car owner functionality, which will change the car owner to Johnny. But again, I just modify this function in a way that basically in the create car, in the change car owner function, we get this verification function. So basically, if I know the correct input and if I can give a proof of the correct public input, and then I can change the owner of the car. If I cannot do it, then I can't do it. So let me do it. And basically, what I will do here, that's gonna be theoretically a wrong proof. I just put the wrong number. So if I put the wrong proof, then I get the unauthorized error. And then I can do it with the correct proof as well. So in this example, I have the correct proof. And if I have the correct proof, then basically that looks good. So the chaincode invoke was successful. And then basically, if I just want to query all of my cars, then theoretically what I did, I just changed the car owner from it was something which is Shibohan at the beginning. If I'm not mistaken, that was like Shibohan. And then that should be like Johnny. So that should be like owner Johnny. Okay, so that was the simplest example. I would say I will just stop like 2 minutes and try to answer some questions if I manage. I'm not quite sure if we will cover the other 2 examples in details. I mean in live, but I will just highlight a couple of ideas so you can do it actually on your own as well. But let me just take a look on chats. Yeah, so I mean, there's a question how can I change like the inputs? So it looks that way, like, you know, I mean, there's like the So there are like two JSONs. That's the input JSON, and it looks that way. That yeah, I can do it. So it's like, I don't know. We say free, and then of course we need to be consistent with the expected code. So that's gonna be like, I don't know, 21. So if I just say free and 21, that should be a correct 27. Sorry, 27. It's just difficult for me to speak and to think parallel. It's just not possible. But anyway, so yes, sure. So if you have like a consistent combination, so you say like free and you say like 27, then of course you can create a new proof basically that's gonna be correct. You're gonna have like the public inputs values, that's gonna be like 27 in our examples, and everything works similarly as previously. So basically you can have all the integration with JavaScript, with Solidity, and basically with Hyperledger Fabric as well. So that's yeah, I have to generate the proof, yeah, when I change the input, yeah. How can we trust the verifier code if it relies in an obscure verification keys? So basically, I mean, the verification key is generated by Circom. So it's a good question. In some sense, we need to trust the environment. So as a developer, there's no good way of, I mean, somehow saying that we should verify actually the framework for Circom. I mean, if you're a mathematician, you might as well do it, but I mean, it's Rust program. So either we verify how Circom generates actually the verification key, or we just trust them basically. I mean, the compiler that I can. So basically, I mean, what you can do if you just take a look on the demo, basically that's like, I mean, you can just change this. So what you can do, you can just start basically from a demo, like from this one, and then say, hey, let me just put some more inputs. It's like gonna be like there's a B, and then basically we don't do like a cube, but we say like, hey, that's gonna be like A times B, and it's not gonna be a cube, but it's gonna be like A times B times A. And then you can just compile again, and then basically you can have the whole integration. You can replay the whole integration. That's possible basically. Can this circuit estimate from Hyperledger smart contract percentage will calculate the from Circom without revealing the value fix? We start in the same. So I'm not quite sure if there's like a more complex example. Again, it's just difficult for me to speak and think in the same time. But basically, you need to prove you want to prove some input, some hidden input calculation in Hyperledger Fabric. So that's what you can basically use. You can integrate in a JavaScript. Chain code, basically a verification function, and then you just have the verification keys, which is practically somewhere here, and then you will have just the inputs, and then you have the proof. So basically, any calculation that you can manage in a way that you get some private inputs, some public inputs, you just build the computation model with Circom, and you just put the input and the proof to Hyperledger Fabric. It's doable. I'm not quite sure it's just, yeah, it's like XY, Y is more tricky with Circom, but it's doable. It's just you just need to research a little bit on the internet. So let me just continue with some more audios. We just not gonna go and see again all of these demonstrations, but basically I will just make some hints and you can evaluate on your own. Let me just basically bring down shut down Fabric. It's something wasn't killed, but it's just specific. So let me just make sure if it's deleted. Set like a point. Yeah, looks good. So let me just continue, and basically we just not see this demo in details for the following examples, but they work pretty similarly. Okay, so we got the next, that's like the modular Circom. And then for that, what's important is just a little bit like get to know the Circom programming language. So basically, in Circom, what you program like in arithmetic circuits and rank 1 constraints. So basically, that's kind of an x plus epsilon times z equals or must equal v kind of logic, which is, yeah, sometimes not the easiest one to program, but at least you get basically an idea how like programming in real zero knowledge looks like. You can have like higher level zero knowledge programming languages as well, but the problem with higher level zero knowledge programming languages is that although the abstraction is higher, but the security is questionable, and the size of the generated circuits is much higher. So that's the problem. So you program with rank 1 constraints and arithmetic circuits. It's like rank 1 constraints is like alpha times beta equals gamma, where this alpha, beta, gamma, that's like a fine combination of variables. What's important to know is that these are like hardware description languages, or similar to a hardware description language. What you do in a hardware description language is that normally you program circuits. So you have like one circuit, this is like one circuit, it has some input, it's like input, and it has some output, and then basically you can have the next circuit, that's the next circuit, and it has some input and some outputs as well, and the third one, and so on and so forth. And again, so the easiest example, these are just gates, like AND and OR gates. And these are inputs, and at the end you have some kind of basically an output, but basically you say that this output like should be equal to another input as well. And then if so, then we have practically a predicate. Okay. So that's like programming in circuits. It's a little bit tricky. It's not an imperative language, but if you ever seen like VHDL or classical circuit programming, hardware programming languages, that's pretty similar. So we got here signals, we got here gates, we got here wires, we got here sub-circuits, and then we can just connect and wire circuits and gates. So we just define these circuits or gates, and we just make this wiring basically. That's what circuit for the first run all about. The trick is, or just to have like a higher abstraction, we can have a template and the template programming language as well for sub-circuits. So we can define kind of an abstract circuit. It's called a module, and then we can just create like even with a loop several from these sub-circuits. So we can have something which is variable and control structures or loops, but it's important to note that on a low level you just program these gates, you just wire these gates, and as a higher level language construct, that's only for a template programming language. So at the end you generate like a lot of, so you use the template generation language just to generate these circuits and wire these circuits dynamically on a higher abstraction level. That's another perspective. It's again, we get just these rank 1 constraints, which is circuit programming. So we had like, once we have assignments, that's like more like an arithmetic circuits, and then it states that like x times y z gets the result for x times y. We can have basically like constraints which says that z must be equal in all circumstances the result of x times y, and then we can have basically both. That's both an assignment and the constraint as well. So that's basically what we use on a low level in circuit programming. We usually use components. So these are like the components what we use, and then we have also a main component. So if I just go back to the Hello World application, what we're gonna have is like our main component, That's our demo. So based on this all stuff, basically we just create one component which has some inputs, and some inputs are public and some inputs are private. So that's what we have basically at the end. That's like the main component, and we use just the main keyword for that. And then we get this, what we call here as template language. That's kind of meta programming. We can call it as a meta program. Again, we can have like variables, but the variables are evaluated in compilation time. So basically the whole idea for this meta programming, for variables, for loops, that basically at the end, there's gonna be a circuit which is generated. So like we can have loops, but these loops evaluated in compile times and generate basically a fixed circuit. So basically we can have kind of a fixed loops. And then there's like a couple of special non-intuitive rules how you can like mix variables and signals basically. And there's ways of like embedding one circuit to another one. So basically my second example looks that way. If you go to the second example, that's like modular Circom. What I'm using here is a modular circuit. I just have a couple of sub-circuits. So basically, I have this compute.circum, which is a sub-circuit. It has like input A, input B. It has an internal signal, which is calc, and it has one output as well. And it just computes kind of a internal calculation as A times A plus B. And then it just multiplies this B with this calculation, and that's the output. Okay, but that's like a sub-circuit, like this guy here. And then I have another sub-circuit as well, which should be like the power. And power is more tricky because it's actually not just a sub-circuit, but it's a template. So this one is a template. It has a parameter n. So basically it's gonna generate n circuits. And this n is a parameter, but it's evaluated in compilation time. So what we can do, we can like generate like 100 power circuits with that in a sense, or we can generate like thousands. But what we can't do, we cannot leave this undefined. So in compilation time, there must be known how much like circuit is generated. Okay, but again, it's not exactly true that the circuit is generated. It's big because it's basically a parameter that can be set to a fixed number at compilation time. And it has basically an array of signals. Usually there's no array, but what we can have, if we just define it that way, that's again kind of a meta programming trick. Then what we do, we just create n pieces of signals. So basically we just set this one in compilation time. Then if we say, then there will be like n different signals. And we just create a for loop, which basically internally calculates, like multiplies the n signal with an internal calculation, and it just gives back the output. What it basically does, if we have like such a for loop in our meta programming, then basically I have like I have like a for loop for 5 parameter. Then basically kind of a sub circuit will be here generated five times. Okay, I can have this guy like for 10, then this sub circuit will be generated kind of 10 times. Okay, and that's what's here happening. I'm just not gonna go very much deep into the details of the exact wiring, but basically this is like not a real sub circuit, but it's kind of a parameterized sub circuit, or practically we use like meta programming, having one parameter which is set in compile time, and then you can generate more dynamically circuits. And I got this modular.circum, and modular.circum basically looks that way, that it uses these components. So it's basically a circuit itself. It's a circuit itself which uses like one circuit that I defined here, that was like the compute.circuit, and it uses like another circuit which is parameterized in a way that we can use it like 5 times, and then it defines one big circuit which embeds these guys and wire them somehow. Okay, so that's what we have here. And basically it looks that way. This guy has some input and some output as well. And then basically, so these are like the inputs for the big circuit, and we get some outputs for the big circuit. And then what we have here, we just use this component keyword. And basically what we do here, we just wire the internal components. We just wire for the first one this compute internal circuit, and then we just create basically a power which was this general parameter. We just create this one with the template number of 2. So we just create 2 sub-circuits from them, and we will wire basically this one as well to this main component. And basically based on this main component, there will be like one big circuit which has like a couple of sub-circuits, and with that we just create one complex computation. Okay, so that's the idea of Circom programming in like, introduced in like 15 minutes. It was very compact. So I would just stop like, I don't know, 2 minutes and then try to answer questions. Anyway, what you can do, you can have like a full Circom tutorial. The plan wasn't like having a full Circom tutorial. The plan was just create like, an idea how more modular Circom zero-knowledge system looks like. But anyway, if you have like the same structure, so I mean, if you just take a look basically on the README, you can exactly do the same thing that we did for our simplified circuits. So you can run. Run basically creates the power of tau setup. It creates basically the proving and verification key. It just creates basically all of the cryptographic materials. And then after that, you will have basically a test proof and test verification. And you can do the same thing basically with Node.js, with Solidity, and with Hyperledger Fabric as well. The same way, one exception is that our computational model was changed. So we have practically this more complex modular computation. So I will stop just for a second, and then I would just introduce the last example, which is going to be more tricky. Values can come from smart contracts. If the signal values from circuits can come from smart contract in Hyperledger Fabric instead of being hard-coded. Yeah, that's a good question. Yeah, I mean it's possible. It's doable. Theoretically, I mean you can even generate the proof in Hyperledger Fabric as well. So you can do everything in Hyperledger Fabric. The only problem is that so you can do something that you generate the proof in Hyperledger Fabric and you verify the proof as well in Hyperledger Fabric. So practically everything can be in chaincode, even the proof generation and public and private signals. The only problem is that so proof generation might take time, like a couple of minutes. So it's just not necessarily practical to run it on chain. But technically, I mean, especially with Hyperledger Fabric, you can have such scenarios that like defining an organizational privacy. Like one organization should see something and the other one not. And it's like, like one organization in like I don't know, in one channel just compute something, and another organization in a fully different different chain code gets basically the results and verifies. So it's doable with Hyperledger Fabric. The only thing is, again, so if this model getting to be more complex, then you have a problem because the proof time can be huge. I mean the proof time not necessary, but the effort for proof can be huge. So like I got like, I don't know, with big computations, I mean on the one hand it take like, I don't know, 10 minutes or 20 minutes, but like your proving keys can be huge as well. because of the power of tau. So you just make I mean, it's just, you know, careless engineering if you manage it basically or not. Okay, sorry, careful engineering. So yeah, that's an interesting point. And then, so I will have some more. I'm not quite sure how much time we have, but let me just continue like 5 to 10 minutes, and then we stop for the end. So basically, what we have here in Circom, that is so-called Circom lib. And the problem is it's just not very practical, basically, to program everything from scratch. I mean, especially if you need some, you know, I mean, cryptographic materials. But even if you need, like, you know, simple use cases, programming in circuit might be tricky. So for this reason, you have the Circom lib, which has some predefined templates and predefined circuits like AND or NOT, multiplexer, comparisons, like these are like basic circuits, but some cryptographic primitives as well. So like EDDSA signature, like Pedersen commitment schemes, hash functions, and so on and so forth. So if you want to use Circom in real life experience, then you might as well consider this Circom lib, and then use some of the predefined and tested circuits. Perhaps one more point, just going back to this modular Circom example, basically it looks that way, that so if you just create such computation models, then, so let me put it that way, it's sometimes not intuitive, and sometimes it's just not very easy to debug. So usually what you do, you use it somehow in a test-driven development basis, and you just make sure that you test like all the subcomponents. So if I have like one component here, like compute, if I had the other component here, which is like power, then before I just integrate them, I usually just make sure that they are like tested and they really do the job that they need to do. And then for that, there's like one good GitHub repo, just like the Circom tester. It helps you actually implementing tests, but you can use like Mocha and Kai and some other frameworks as well, basically testing your sub-circuits. But it's typically a test-driven development. And then one more thing, that's the last thing, but basically we did not really have time. So I'm not quite sure if we just continue. Let me have it that way. The third example is a very much simplified rollup, basically. I mean, not cover the code, but you can take a look. If you take a look at the third example looks that way, that in the run script, basically the power of tau is commented. So you have just one command it's because that's a big circuit. So what I need to do, basically, I just need to have like run this like 3 hours on my laptop. It's because I would probably need, I'm not quite sure, that shouldn't be like, no, it's okay. It's not 3 hours. It's just like 10 minutes. The point is I should have like here 14 bits power of tau. I hope that's enough. If it's not, then you need like 18 bits power of tau. Then that's gonna run like 3 hours. So you just need to uncomment this and experiment a little bit if 14 is enough, or if you need like 18, and then you just need to generate it, which can take like, you know, from 10 minutes if it's 14 up to like 3 hours if it's 18. It is because if the circuit is big, and you know, a scenario in this off-chain transaction, that's a big circuit, then you need like a higher bit number. But this last example, there are like a few slides. It's a very simple roll-up experiment, I would say, which looks that way. What I usually have in a roll-up, you try to run basically transactions out of your blockchain, but you want to create basically some cryptographic proof, especially a zero-knowledge proof, that that this execution off chain is correct, and put that result to the blockchain. So what we have here, basically, we got the blockchain and we got a coordinator, which is like a rollup system, which is totally off chain, which basically stores balances of different people or different accounts. So we got here like Alice, Bobby, and Mallory. They are identified with a public key in a very simple case, and they have some balance. Okay, but they are not in the blockchain, but on a coordinator, and then the Merkle root basically is written into the blockchain. So again, this one is the blockchain, and the other one is the rollup system. So what we have, we just want to execute a transaction off chain on the rollup system. A transaction is very simple. I just want to transfer money or crypto from Alice to Bob. So basically, my transaction looks that way, that I have a public key, which is Bob, or which is Alice. I have a public key, which is Bob, and I just have an amount. So what I just want to do, I just want to decrease the balance of Alice with the amount. I just want to increase the balance of Bob with the amount, and I just want to make sure that's a correct signature. That's what I want to use. But again, everything is basically off chain. So what I practically do, I will just write a zero-knowledge proof on this whole computation. I have the old Merkle root, I have my signature, and I create basically a zero-knowledge proof that there was that's the transaction. That there was a transaction on this old Merkle tree that basically said Alice wants to transfer an amount of money to Bob. It was basically signed by Alice. Again, everything I prove with zero-knowledge proof. I just decreased the balance of Alice with the amount. I just increased the balance of Bob with the amount, and I created a new Merkle tree. And then basically, I just put basically the Merkle root of this new Merkle tree with the modified balances to the blockchain with a zero-knowledge proof that I had such a correct transaction. So that's what an off-chain execution looks like, basically, and that's kind of a very, very high-level basis for zero-knowledge executions on zkRollups. And you will find one such a very simple example here. Again, it's just we will have like one circuit, that's this transaction circuit, and then basically it looks that way, that it basically uses some sub-circuits. But what I'm having here is that I just verify, I will have a transaction, again, which transfers money from Alice to Bob. I just verify if the sender account exists on the account root, on the Merkle tree. I just hash basically the transaction and check the signature, check if that transaction was really signed by Alice. In our example, I just debit the sender account, so I just decrease the balance from Alice, and then I will just I will have one intermediate proof here, but it doesn't matter. I will just credit Bob's account, so I will just increase the amount on Bob, and I will just create one more account root, one more Merkle tree root, and I will just publish this new Merkle root with practically with my zero-knowledge proof to the blockchain, and that's what a very simple zero-knowledge roll-up has as a basis. Usually, you don't just execute one transaction, but many. But that's the basis on a high level for a zero-knowledge roll-up. So I have 5 minutes more. It was taking a little bit longer than I expected, although I try to speed up as much as possible. So yeah, questions, I would say. Again, I just try to introduce these examples in a way that you can just experiment with that on your own as well. So again, just if you have like hello world and modular Circom, everything should work as it is written in the README. With the rollup, the only thing which is tricky is that you just need to generate this power of tau. I think I used some pre-prepared power of tau, which is not in the GitHub repo because it's just a couple of hundreds of megabytes. So it's just not practical to push in. So you just need to generate it. But if it is generated, then basically you can use everything as it is written basically in the README. So, are there any questions? András is here as well. So if you have like cryptographic questions as well. So I'm just browsing. Sorry.
Yeah, we've got some questions in chat.
Yeah, I'm just browsing basically the chat. Yeah, we are just browsing. I think we answered already a little bit this question. Yeah, that's like the not secure obstacle verification key. Yeah, it's just if it's possible to integrate. Yeah, that was the file exception. Yeah, so there's like question. I want to prove something. Which part of the public inputs are variables in blockchain itself? Yeah. So again, we used like this model for our demonstration. That you do some off-chain calculation, which is clearly not on the blockchain. So basically, your input variables, your private input variables, especially, are not in the blockchain, and you do just the verification on the blockchain. But there might be other models as well. Again, what I was brainstorming. So if you want your full private input, for instance, in one channel, and you want to verify another channel, it is doable. If your computation is not too complex, because if so, then the proving time will be huge. But again, for the demos, that's the model that we use. We just have something off chain. So basically, we don't use like for our inputs variables in the blockchain. Just there are some guys out of the blockchain doing some private input and then want to prove that they know that private input and then want to make basically a proof of it. But yeah, again, this is just one architecture model, especially with Fabric. You can just combine it as much as you want. Yeah. So I'm not just sure. I'm just browsing the questions, but we have like just a couple of minutes. So if you have like any question, yeah, just go ahead and I don't know, unmute yourself, just ask or just put the end of the chat because I'm just lost a little bit on this too many questions.
Yeah, if you have a question, feel free to put it in chat. We can't unmute everybody, but please put it in chat. We can save the chat and put a text file in the wiki page as an embed. So great idea, Xavier. I'm happy to do that.
Yeah, so one option is actually that I mean you can just reach us after the presentation as well. So basically you can find us on LinkedIn. So I would say that if there's any questions that comes later, or perhaps we just didn't pay attention here, then yeah, just feel free to ping us on LinkedIn. Yeah, absolutely. Yeah. Yeah, there's one question. Do we check the standard digital signature in the circuit? Yes. There's a digital signature check as well. It looks that way, if I'm not mistaken. There should be somewhere. There should be like an EDDSA signature, and then what we use is basically we use self-defined, but basically there's like a Circom, circumlib. So you get this circumlib, and in circumlib you have like one circuit which is ADDSA, and with ADDSA circumlib functionality, you can check if somebody created a correct digital signature with zero knowledge proof without actually knowing the signature itself. Yeah, absolutely. Yeah, but again, so I would say we are just getting tired, honestly. So apologize if you just, I mean, perhaps didn't answer one or two questions in details. But I would then encourage everybody just ping them on LinkedIn, and then we can answer all of the coming questions, or all of the questions that we coincidentally missed.
Outstanding. And folks, I just posted in the chat both the wiki page for this workshop as well as the link to the YouTube. That is for the live stream. It will also be the permanent link for the YouTube video itself. It's on the Linux Foundation, Hyperledger Foundation YouTube channel under both just under the live tab, but also under the workshops playlist. And at the top of the hour, I would like to thank everybody for joining us. I would also like to thank both Andras and Daniel for putting on such a great workshop. It is incredibly appreciated. Above in the chat, I also included some of the Hyperledger links, like the Hyperledger website, our wiki, and Discord. And Discord is where most of the contemporaneous in-the-moment chats are happening. So by all means, please join us. And once again, thank you, Daniel. Thank you, Andras, for such a great event. Cannot thank you enough for putting this on. I'm not putting my LinkedIn in here. I'm on LinkedIn. You can just search my name because I don't have time. But for folks joining us, thank you, Daniel and Andras. This has been great. And we will post.
Thanks a lot. Thanks a lot for the audience, and thanks a lot for Hyperledger as well, hosting me.
No worries. And with that, I'm going to end the workshop. Thank you, everyone. Have a great day.